Hey guys, today we're here with a special video of deriving Einstein Field Equations, which are really hard to even comprehend, but hopefully I'm just gonna show you their derivation. For that, make sure to like and subscribe, and thank you for supporting me. But you must know that this is real hard to even understand, let alone deriving it itself. So you should know Lagrangian mechanics. You should understand what delta S equals to 0 means. You should understand the action, which is defined as S equals to the integral of Lagrangian with respect to time, where Lagrangian is the difference between potential and between kinetic and potential energy. And you should understand what delta S equals to 0 means here. So I'm not going to explain it in this video because this video is going to be long itself. I don't want to make it longer. But anyways, so the first approach that we're going to make, I'm going to just remind you of a couple of things here. So just let me write you the formula for some identities and things that we're gonna use. So I'm gonna write it in green. First is the Riemann tensor. Riemann tensor. So feel free to speed up the video because my writings are gonna be so slow. So the Riemann tensor is defined as a rank for tensor R sigma rho mu nu is equal to the partial derivative with respect to nu, the Christoffel symbol of sigma nu rho minus partial on nu sigma nu rho plus the Christoffel symbols that we're not going to be worrying about it here because I'm going to explain to you why we don't have to worry about it really, but if you want to really know them, the full formula for a non-vacuum is sigma mu lambda rho nu minus sigma nu lambda gamma lambda rho nu. So this is the definition of Riemann tensor, and these terms here are going to vanish in the vacuum, and considering the space-time locally flat, which I'm going to explain to you what that means actually. So just don't have to be worried about it. So the next definition is Ricci tensor. The Ricci tensor, which is the Riemann tensor with upper and lower indices summed over. So the Ricci tensor is a contraction of Riemann's tensor, which is defined as partial lambda gamma lambda mu nu minus partial nu lambda mu nu plus the Christoffel symbol of lambda mu nu, the Christoffel symbol sigma lambda sigma minus gamma lambda mu sigma gamma sigma lambda mu. So this is the definition of the Ricci tensor. And third is the Christoffel symbols. So Christoffel, I don't know if I'm writing his name correct, but Christoffel symbols, which is defined as gamma L mu nu to be equal to half G K L partial nu G mu. Made a mistake here. Should have written it as. Sorry, gonna write it again. Gamma rho mu nu, which is equal to half G rho lambda, which is a Domet index, partial nu G mu nu plus partial nu G mu lambda minus partial lambda G mu nu. So this is the definition of the Christoffel symbols. And the fourth definition, and the last one of them, is Ricci scalar. I'm gonna write it better. Scalar. Ricci scalar, which is defined as R to be G mu nu R mu nu. So which is the summing up the indices of Ricci tensor with the metric tensor, which is in Einstein's notation, which is actually G00 R00 plus until G44 R44. So this is in Einstein's summation convention. So, but anyways, let's write our action here, which is also known as Einstein Hilbert action. So action, if you've taken Lagrangian mechanics, you probably know what that is, but in general relativity it's a little bit different than classical mechanics, because action is defined as S is defined as the integral of Ricci scalar square root of negative g, which is determinant of our metric tensor, d for x, which means that we are integrating with in space-time, in four-dimensional space-time. So how should we approach it? So this is not an integral where we solve it like as you're used to see in my channels, but rather we're gonna take the variation of this thing here, delta. So delta S is gonna be the variation of these terms under this integral R square root of negative g d to the 4x. And we're taking the variation of this thing here, and just like the product rule of calculus, where we have the d dx of a product, it's going to be u prime v plus v prime u. The variation is exactly like that, the rule of variation. So I'm going to write delta s to be equal to the integral of d delta r root negative g plus delta root negative g plus r and delta root negative g d to the 4x. And delta s, So we can factor out a root negative g here, a factor of root negative g, which is going to make this thing equal to delta r, the Ricci scalar, plus r delta root negative g over root negative g d to the 4x. So first we're gonna work on this one here, the r delta root negative g over root negative g. So as you might notice, this is very similar to the derivative of a logarithm. So delta root negative g over root negative g. So it can be written as r delta, the variation of log of root negative g. So delta log root negative g is going to be 1 over root negative g delta root negative g. So that's where does it come from. So we can move the power down here, which is going to be half r delta log negative g. So here I'm going to use a trick. I'm going to say, so we can say that the determinant of the metric tensor of I pi over 4 and g hat, which is the metric tensor, is equal to negative g, which is the thing that we have here. So the I pi e to the I pi over 4, that is where the negative comes from. So I'm gonna write this again. Half r delta log of determinants of e to the I pi over 4 g hats. So I'm going to call this thing here a hat, and the thing here is going to become half r delta log of determinant of a hat. And we have a identity in our in linear algebra, which says that log of determinant of a is equal to trace of log of a. So I'm going to use this identity here, which is going to be half r delta log of trace, half delta trace of log a hat, and the trace can be moved out here because it's linear, so it's going to be trace of half r trace of delta log a hat, and the variation of the log of a hat, as we see, is like the ordinary derivative. It's going to be the inverse matrix times delta of a, and remember that a was e to the I pi over 4 g. So these, because we have an inverse and a matrix here, these I pi over 4s are gonna vanish, and I can write it as half r trace of the inverse matrix delta g. So it can be written as half r, the trace of this thing is going to be g mu nu delta g mu nu, which is half r g mu nu delta g mu nu, and it can be written as negative half r g mu nu delta g mu nu contravariant version of it. So this is our delta root negative g over root negative g term here. So we've solved this part, so I can rewrite it as to be equal to root of negative g delta r minus half r g mu nu delta g mu nu d to the 4x. So let's go and solve this part here, delta of r. This is a little bit harder to solve, but I'm gonna show to you. So the Ricci scalar is defined, as I told you, as the g mu nu r mu nu, which is an Einstein summation convention, and taking delta of it, the delta of the variation of r is just like the product rule, delta g mu nu r mu nu plus the variation of r, r mu nu g mu nu. So this is the variation that we have to simplify a little bit. So this term is going to go down to 0. So I'm going to prove it why this term is going to go down to 0 and why the variation of Ricci scalar is the variation of g mu nu r mu nu. So let's work on this one, because this is just the only important thing that we have to solve here, and it's very long probably. So delta r mu nu g mu nu, what it is. So before to go, let me remind you of our ansatz here, for assumptions here, that we have a space-time like this. It's a tissue of space-time, and it is curved. It's globally curved, but if you look closely locally here, you're gonna see that like these lines are almost flat lines if we infinitely zoom here, just like the surface of the Earth. For example, a very big sphere, can consider a very big sphere, which is globally curved. So let me write it better. It's globally curved, has a curvature, but if you zoom in locally, we can consider, for example, this very small portion of it a flat space. Therefore, we can use the trick that space-time is locally flat, and the Christoffel symbols, which are the changes in our system of coordinates as our basis vectors change as we move across this space-time here, those are going to be 0, so we have to only take the variation of the Christoffel of symbols, only their variation, so we don't have to worry about themselves. So I'm gonna write the definition of Riemann tensor again, because that's how we calculate the Ricci tensor from it. So Riemann tensor is defined as sigma rho mu nu, which is equal to partial nu, Christoffel symbol of sigma nu rho minus partial nu sigma nu rho. mu rho, sorry. So you might notice that I didn't write the Christoffel symbols, and that's exactly the point. The Ricci tensor didn't write these things because, as I told you, locally spacetime is flat. You don't have any curvature locally in the spacetime, just as you don't feel any curvature locally from your supermarket, from your house to local Costco or local Walmart. You don't have any curvature in Earth, so there is not any change in Earth's curvature. And with that same logic, there is no locally spacetime is flat. Thus, these Christoffel symbols are going to be zero, and only we have to worry about this part here and the partial derivatives that we are taking from these Christoffel symbols here. So what is the variation of Riemann's tensor? So I'm going to take its variation, dr sigma rho mu nu. So if you want to use the product rule, just as before, you're going to get a really ugly result. To make her work more faster, I'm going to use an identity which the delta of the Riemann tensor is defined as the covariant derivative with respect to nu delta Christoffel symbol of sigma rho nu minus Christoffel symbol nu delta sigma rho nu rho mu. So this is these are our definition of Riemann tensor. And what is the variation of the Christoffel symbol here? We're going to use an identity that the variation of Christoffel symbol rho mu nu is half g rho lambda covariant derivative nu delta g nu lambda plus the covariant derivative with respect to nu delta g mu lambda minus covariant derivative nu delta g mu nu. So this is just an identity, and we can plug in the Christoffel symbols here to get a new identity. But we can use another trick, and remember that first let's calculate the Ricci tensor from the Riemann tensor. The Ricci tensor, the delta of the Ricci tensor, if I sum the upper and lower indices of this tensor, it's going to be delta r mu nu, which is sigma delta gamma of sigma mu nu minus delta sigma mu sigma. So what I'm gonna do here, right in here exactly, is I'm gonna multiply this thing here by a g mu nu, as we were looking to prove that this term here is gonna go down to 0. So we wanna prove that this term is 0, so I'm gonna say g mu nu delta r mu nu is the following: delta sigma mu nu minus sigma g mu nu and delta sigma mu sigma. So I can use another trick, and that is to somehow convert and let this be the covariant derivative of sigma. So I'm allowed to do this on the condition of changing the other variables here to nu. So these ones should be nu, this one would be sigma. So this is going to be another, so let me write it again here. So it's going to be sigma g mu sigma delta Christoffel symbol of nu mu nu. And that whole thing here can be factored out to the covariant derivative of g mu nu delta Christoffel symbol of mu nu minus g mu sigma delta nu mu nu. And that is exactly equal to the divergence. That is exactly equal to the divergence, which is equal to, can written be as a covariant derivative of x sigma, and that divergence is going to be zero. Just like you've probably seen that the divergence of energy momentum tensor of 0 is going to be like the same thing here. So this is going to be 0, which means that g mu nu delta r mu nu is 0, and remember that x sigma here is g mu nu delta rho mu nu. Sorry for my bad handwriting because I'm a little tired now of all lecturing you here. So thus we concluded that g mu nu delta r mu nu is equal to 0. Now let's get back to our example, to our action here, which is this one. So let's write delta r here. Delta r was delta g mu nu r mu nu plus delta r mu nu g mu nu plus delta r mu nu g mu nu, in which we conclude that this one is going to be 0. So I'm going to write minus just this term, half r g mu nu delta g mu nu d to the 4x. We can factor out g mu nu. Hold on, we're very close here. We can factor out delta g mu nu. It's going to be r mu nu minus half r g mu nu minus half r g mu nu, or it's negative g delta g mu nu d to the 4x. And this is our delta s here. Now we stated that the delta s, if it is 0, because it's the stationary reaction principle, that the variation of the action would the variation of s to the first order is going to be 0. So if delta s, delta of our action here, which is r mu nu minus half r g mu nu root negative g delta g delta g g mu nu d to the 4x. So if this is equal to 0, so these terms here cannot be 0, only this term here are mu nu minus half or g mu nu, only this one can be 0. And actually I'm gonna call this here big G mu nu. So big G mu nu, which is equal to 0, which is called Einstein's tensor. And if I move it to that side, it's going to be a half or G mu nu, and that is the Ricci tensor in vacuum. And Einstein's tensor is defined as R mu nu minus half or G mu nu here, as you can see in this equation here. So if I multiply both sides by the inverse metric tensor, I'm gonna get half R G mu nu, which is gonna be, this is the definition of Ricci tensor. Ricci is scalar. Half R times 4, this is equal to 4, Kronecker delta symbol, which is equal to R equals 2R, which means that R should be 0. Thus, R mu nu here should be equal to 0 because Ricci scalar is equal to 0. So, what does that mean? R mu nu is equal to 0. It means that we are in, if we were in fourth space-time dimension, it means that we are in vacuum. We are in vacuum. There is no energy and matter here, and the energy momentum tensor is equal to 0. So alternatively, what does that mean actually? So as I told you, it means that there is no energy and matter in space-time. For example, the Schwarzschild solution is a solution to it. So our job is to find the metric tensor, which, if we calculate its crystal symbols, would give us the R mu nu equals to 0. But pay attention, it doesn't mean that there is no curvature in space-time. Yes, if the Riemann tensor was equal to 0, that means that the space-time is flat. But the Ricci tensor is equal to 0 doesn't mean that space-time is flat. It means that we're in vacuum. So in next videos, I'm gonna show you how we can solve the metric tensor for which the R mu nu would be equal to 0. For example, a Kerr solution for rotating black holes is a solution to it. Flat spacetime is a solution to it. Anything that does not involve a spacetime with energy and matter would be a solution to it. So I'm gonna write the full Einstein field equations here for you. Or, so let me write it this way: R mu nu minus half R G mu nu plus lambda, so I'm going to write the lambda like this, plus, plus lambda G mu nu is equal to 8 pi G divided by C to the 4 T mu nu, which is the energy and matter here. This is cosmological constant, but basically it's the simplest representation of vacuum energy and expansion of universe. This is the Einstein tensor, which is the geometry of space-time. And when we set T mu nu equals to 0, which means that there is no energy and matter, and we set cosmological constant equal to 0, we're going to get R mu nu is equal to 0 in 4-dimensional space-time. And that is the final form of our Einstein field equation, which was derived by Einstein-Hilbert's action. Thank you for watching this video. So you've seen that we have done lots of work here. If you enjoyed, please like and subscribe. So next videos we're gonna solve the Einstein Field Equations for the metric tensor in four-dimensional space-time. Make sure to like and subscribe, and I'll see you next video.